Well, thank you very much, Stuart, and for reminding me of how old I am. Also, thank you for collaborations recent years. We've worked together, and I'd also like to acknowledge my other collaborators, Vladimir Mujica, Vin Pizziconi, and George Wolf. So this is the cover slide, the cover picture, and it contains my outline. So basically, I'll talk about experiments, theory, and applications of nanothermodynamics. But also on this slide, I have some background information that might be useful to sort of lay the groundwork for what I'll be talking about. So today I will talk about something relatively new in equilibrium thermodynamics. By relatively new, I mean it's only 63 years old. But in a field that was thought to be essentially complete 149 years ago, 63 is not so old. Another thing I mean by this is that very few people I meet, almost no one has heard of Terrell Hill and his theory of small system thermodynamics. And I find this strange because it's very similar to the additions that Terrell Hill made to the fundamental equation of thermodynamics are very similar to what Gibbs did. And every one of these physicists that I meet has heard of Gibbs. So why is this? Why have people heard of Gibbs and not of Terrell Hill? So to explain how the fundamental equation of thermodynamics has been modified, this is the fundamental equation of thermodynamics. It's basically conservation of energy for reversible processes. This is heat, this is work for reversible processes. This is the chemical potential, which Gibbs introduced, and this is the subdivision potential, which Hill introduced. So the chemical potential, this is the number of particles in total in the system. It generally applies to large systems. So when capital N gets big, this is important. Eta is 1 over the size of the system, roughly. So this term gets important when the system gets small. So of equal importance, mathematically similar, of equal importance, everyone's heard of Gibbs, almost no one has heard of Terrell Hill.
Did Hill live for 2 years only?
That's the years that he produced this work. Sorry. No, he lived to be 96. He was quite a prodigy indeed, yes. Yeah, so sorry, these are the years that he published. So he published 1 paper and 2 books on the topic. And most of what he was interested in is systems that were out of equilibrium, biological systems and nano-fabricated systems, things like that. He was interested in them because, the thermal equilibrium of life is death, and the thermal equilibrium of integrated circuits is basically sand on the beach. So they are important to be held out of equilibrium. What we're interested in is the thermal equilibrium inside of materials. So rather than on the surface for nanotechnology, we're interested in what happens inside samples, inside materials. And so we're interested in the equilibrium, the stable equilibrium of small system thermodynamics. And that turns out to be only 1 section of 1 chapter of 1 of his books. So a tiny fraction of his total output on small system thermodynamics deals with the stable equilibrium of nanometer-sized subsystems inside of larger systems. But that's what I'll be talking about today. And using those ideas, we've been able to solve 6 or more problems, resolve, or at least provide insight into 6 problems, at least 3 of which are considered unsolved problems in physics, such as the liquid glass transition, 1 over F noise, and Loschmidt's paradox for the arrow of time. All from this 1 small section of Terrell Hill's work. So we became interested in this when we made an experiment about 30 years ago. It's called non-resonant spectral hole burning. It's where you pump energy into a sample and look at what happens to that energy. It turns out that energy stays in the slow degrees of freedom and does not go to the heat bath quickly. So this is a heat resistor that keeps the temperature of the slow degrees of freedom different from the bath temperature. So standard thermodynamics is based upon the assumption that you have homogeneous and infinite systems, whereas this experiment showed that you had small systems with heat that did not transfer quickly to the heat bath. So I've been accused of being a chemist for being concerned about thermodynamics rather than statistical mechanics, because most physicists believe Boltzmann's factor is the foundation of thermodynamics. But in fact, the fundamental physical laws are in the thermodynamics, and you have to understand those fundamental laws in order to get the statistical mechanics right. And so, of course, we're not the only physicists to be concerned about thermodynamics and the foundations of Boltzmann's factor. So Feynman also said in his book on statistical mechanics, he calls Boltzmann's factor a fundamental physical law, but then he goes on to, in the next sentences, talk about all the assumptions that are involved in the fundamental physical laws. The system must be very weakly coupled to a bath. So it must be weakly coupled, but essentially instantaneously coupled to an effectively infinite system. And this experiment shows that that's not true. That these temperatures can be different than the heat bath for seconds or even hours, so that the system is not quickly coupled to the heat bath. And so what temperature should we use in Boltzmann's factor? Should we use the local temperature of the fluctuating system, the temperature of the bath, or something in between? So that's sort of a question that arises. As an example, consider molecular dynamics simulations. So the first molecular dynamics simulation was a test of whether or not it would obey statistical mechanics. So a linear chain of the Fermi-Pasta-Ulam-Singhal problem, a linear chain of atoms. Does that system approach thermal equilibrium? It was found that it did not. It did not obey the equipartition theorem, but it's now known that that system was too simple. And so if you make it, so there are various ways of defining temperature in a molecular dynamics simulation. You can define it by the average kinetic energy, the average potential energy, or the fluctuations in kinetic energy or potential energy. And they should all be the same. If statistical mechanics holds the same, you should get the same temperature for all of these different quantities. Well, you do get this, for a complex enough system, you do get the same temperature for the average kinetic energy and the average potential energy, but what about the fluctuations? So here for this simple system, Leonard-Jones potential or nitromethane, the fluctuations in potential energy are 10 to several thousand times higher than the fluctuations in kinetic energy. So these fluctuations, these are, if Boltzmann's factor applied to this dynamics, these should be the same, and yet they're off by orders of magnitude. Therefore, the effective temperature of the potential energy degrees of freedom can be 5 to 50 times hotter than the effective potential temperature for the kinetic energy degrees of freedom. So this, I won't show any more molecular dynamics simulations, but it is related to Loschmidt's paradox, because molecular dynamics is intrinsically reversible. It's based on Newton's laws. And the model we'll show later also can be reversible or irreversible. And we'll show that it has to be irreversible in order to maximize the entropy and therefore confront Loschmidt's paradox. Okay, so that's the background. This slide is the experiments that produce evidence for the importance of nanothermodynamics. So most of these experiments are based upon specific heat measurements as a function of time, where you put a heat pulse on one side of the sample and measure the temperature as a function of the time on the other side of the sample. So that's shown here, measurements made by Michael Meissner and co-workers at the Hahn-Meitner Institute. And so this is temperature difference as a function of time on a logarithmic time scale, milliseconds, seconds here. And what do you expect? Well, 324 years ago, Newton introduced his law of cooling. So what he found was that the temperature of a system recovered exponentially towards its equilibrium temperature. He determined that experimentally. Can anyone tell me why he was interested in this experimentally? Think about cooling of gold and silver.
See, an alchemist.
He was, but he was also the head of the Royal Mint. And so he was concerned about how things cooled off, and he measured this experimentally, and he understood where it came from because he had invented calculus. Okay, so that's what you expect. You expect the heat go up as the heat diffuses through the sample to the thermometer, stabilize at a value which is inversely proportional to the specific heat. A small specific heat has a large temperature jump, a large specific heat has a small temperature jump. Then it should return exponentially to zero at a long time. An exponential looks like this on a semi-logarithmic plot, so not what you're used to. Okay, so here's the experiment. It does not recover exponentially. It does at long times, so that's the heat coming out of the sample. There's the diffusion through the sample at short times, but at intermediate times, the heat is flowing from one part of the sample to the other part of the sample. And by the second law of thermodynamics, the only way that can happen is if there are different temperatures inside the sample. And so that's where we create this cartoon picture of different temperatures with different heat resistors coupled to the heat bath. And these different regions presumably correspond to the different things that are measured. This is an NMR experiment that measures the slow and fast degrees of freedom and the length scale of these things inside of samples. Okay, so that's the specific heat as a function of time. What about as a function of temperature? So these are dielectric materials. So at low temperature, we expect Debye's law for the specific heat, T cubed. This is a silica glass measured at really low temperature. And you find that it does not obey Debye heat capacity expected. It's several dozen to several hundred times higher. So this lower value is the starting value. This higher value is the equilibrium value at what they could get to at the longest times. So at the starting value, it's maybe a few dozen times higher than expected from Debye theory, but at long times, it's several hundred times higher than expected from Debye theory. So there's something other than plane waves going on in here. So Debye theory is based upon plane waves, the heat capacity of plane waves. This is something else, something localized, something other than plane waves, anharmonic degrees of freedom inside the sample. But this was a glass. You can also make measurements on quartz crystals, ultra high purity quartz crystals, which is chemically the same, just a crystal rather than amorphous. And you find that the crystals agree with Debye's theory, but only at short times. The long time thermal equilibrium is maybe an order of magnitude higher than the predicted by Debye. So there are also anharmonic modes inside crystals, ultra high purity crystals. Yeah. This is 1 Kelvin. Sorry, they're cut off on this zoom. This is 1 Kelvin. This is 0.1 Kelvin. This is 10 millikelvin. That's about, sorry? Vertical is in these units, joules per gram Kelvin. And yeah. Okay. Anything else? Thank you. Okay, so of course, for the crystal, they cross over here in the millikelvin range, and by 1 Kelvin, the harmonic modes are much larger. The anharmonic modes are maybe 1% of the harmonic modes. By room temperature, they're parts per million. Parts per million. This slow response, parts per million of the harmonic modes. So you might think that's negligible, but if you're making a measurement as a function of time, or if you're interested in the thermal equilibrium at long times, it's 100% of the slow response. So it's still significant, even at room temperature, these slow degrees of freedom, if you're interested in the anharmonic modes inside the sample. Okay, so this is what inspired our experiment that we introduced about 30 years ago. Instead of putting the heat pulse on the heat bath, we will add extra energy to the slow degrees of freedom by putting on a large amplitude pump oscillation in a field, such as an electric field or a magnetic field or a strain field, and then probe the sample to look at its response as a function of time. And then by using phase cycling and so forth, you can get rid of all the linear response, all the fast response, and focus on the slow degrees of freedom that are modified by this large pump oscillation. So we think of it as effectively heating these slow degrees of freedom. And by changing the frequency, you can change which slow degrees of freedom you put the energy into. And then you can observe what happens from this extra energy added to the sample. Of course, you can't use a thermometer on the heat bath because the heat comes slowly from the slow degrees of freedom. So we, instead of using a thermometer, we use the time scale of the response. And by Arrhenius law, the change in temperature is proportional to the change in the logarithm of the time response. And so we can convert the change in time scale of the response to a temperature. And so here's a measurement on propylene carbonate at a temperature near the glass transition temperature. And what you see is when you put on a 2 Hertz oscillation, a high frequency in this case, the slow degrees of freedom are modified most. They're heated most. Temperature difference of a few millikelvin, that's 0.1% of the temperature. If you put on a low frequency, that's 10 millihertz, then the degrees of freedom, the slow degrees of freedom are modified most. And if you put on an intermediate frequency, the intermediate frequencies intermediate timescales are modified most. So this directly establishes this extra heating and virtually no overlap between the degrees of freedom that are modified by the high frequency and the low frequency, indicating that these degrees of freedom are completely independent of each other. Therefore, their entropies will be additive, which is the crucial ingredient for nanothermodynamics. Similarly, for a spin glass, with a magnetic pump and a probe, we find that there's virtually no overlap between the high frequency, in this case 30 Hertz, and the low frequency 30 millihertz. So again, not only in liquids and glasses and spin glasses, but also in polymers and crystals, this seems to be a very general phenomenon. The foundation, the basis of nanothermodynamics is that you must have independently fluctuating subsystems inside of the bulk sample. So that's the experiments. The next slide is a theory. So with this one slide, I will present all of what I think are the key ingredients in nanothermodynamics. But it's a complicated slide, and so I'll start slowly. Go back to standard thermodynamics and statistical mechanics can be derived by ensemble theory. So in standard thermodynamics, you have large systems that form a large ensemble. The systems have to be large enough that their surfaces can be ignored. And so all you worry about is the interfaces or the walls around each system. So if you have thick walls, no heat comes in and out, the number of particles, the volume, and the energy are fixed, that's the microcanonical ensemble. If you have thin walls so that energy comes in and out, energy fluctuates, heat comes in and out, energy fluctuates, and temperature replaces energy as an environmental variable. That's the canonical ensemble. If you have holes in the wall so that particles come in and out, the number of particles fluctuates, and chemical potential replaces the number of particles as an environmental variable. That's the grand canonical ensemble. If, as the particles join or leave this region, you want to keep a constant density rather than a constant volume, then you have the mu PT, or generalized ensemble. This ensemble was introduced by Guggenheim in 1939. Prigogine, the first Belgian scientist to win a Nobel Prize in science, he pointed out that this is ill-defined in standard thermodynamics because these are different Legendre transforms. You take away the heat energy, you take away the chemical energy, you take away the work energy, and you have nothing left. There's nothing left to describe the sizes of these systems. And so that's what Hill did 63 years ago, is he introduced this new pair of conjugate variables, the subdivision potential and the number of subdivisions, so that when you take away all these things, that's what's left. That's what controls all the fluctuations inside of a bulk sample. So eta is just the number of subdivisions. In all these cartoon pictures, it's 9. Epsilon is the subdivision potential. So you can understand the subdivision potential by comparing it to the chemical potential. The chemical potential is the change in energy to take one particle from a bath of particles into the system. The subdivision potential is the change in energy to take not a single particle, but a cluster of interacting particles from a bath of clusters into the system. In general, 5 interacting particles have different energy than 5 isolated particles because of surface terms, length scale effects, fluctuations, etc. 5 interacting particles have different energy than 5 isolated particles. For the first time, you can include that energy from interactions and fluctuations on the nanoscale in thermodynamics. Another way to think about this is to look at this cartoon picture. A simple 3 energy level system and how you can change the energy of that system. So this is a distribution of this is, sorry, it's cut off, but this is different energy levels and the occupation at, say, a given temperature. You can change the energy by adding heat, which changes the distribution of occupations of these levels. You can change the energy by doing work, which keeps the same distribution of occupations, but changes the spacing of the levels. You can change the energy by adding particles, which keeps the same distribution, just increases the occupancy of each level. Or you can change the energy by changing the size. So if you make a system small enough, you'll have surface effects, you'll have length scale terms, you'll have surface states, you'll have fluctuation terms, et cetera, that will broaden these levels. And so for the first time, you can systematically include this contribution to energy in thermodynamics with Hill's subdivision potential. So that was his, he derived small system thermodynamics based on the idea that small systems, if you have a large enough ensemble of small systems, it must behave like a large system. And so that was the foundation of what he did. So he brought together many small systems and imagined that they must behave like a large system. Nanothermodynamics is sort of the opposite. You imagine a large system that subdivides into smaller subsystems. It's mathematically equivalent, but conceptually it's quite different. So you might wonder, what would cause a large system to subdivide into smaller systems? Well, it's usually entropy. And you say, wait a minute, we learned in kindergarten that subdividing a big system into smaller systems usually reduces the entropy. Literally in kindergarten. Remember, a big box of toys was messy and a bunch of little boxes of toys was much neater. Well, that's true only in the canonical ensemble. So here's a simple system with 2 indistinguishable particles in it, semi-classical ideal gas particles. There's one way to have both particles on the left, one way to have both particles on the right, one way to have one on the left, on the right. There's only one way to subdivide that into the canonical ensemble, so the entropy is represented by the multiplicity, the number of different ways. So the entropy goes down when you subdivide it into the canonical subsystems, but it goes up when you subdivide it into nanocanonical subsystems. The subsystems can be of any size, have any number of particles in them, and so there are more ways to do that than the original bulk system. So what are these walls? They aren't real walls inside of a sample. What they are, what we believe they are, is exchange interaction and indistinguishability. So these 2 particles in the same box are indistinguishable. They have exchange interaction between them. These 2 particles in different boxes are distinguishable by their location. So that's another thing that adds to the entropy of the small systems, is that the particles are distinguishable by their location, which increases the entropy. Okay, so that's the foundation of nanothermodynamics, the theoretical foundation. Next, I'll start working with examples. Questions? Okay, so the first example I'll work with is. Yes.
I read a lot about this. You use the word exchange interaction, which I would think was explicitly applicable to magnetic systems, but of course this is a much broader theory that applies to glasses and so on. So is there a generic equivalent of the exchange interaction?
Maybe I should have just said quantum exchange. Somehow the particles, it's whether or not the particles are distinguishable or indistinguishable. So I think of it of them having to be close enough that you can't tell them apart. And so you could exchange their positions and not know which was which. That's what I think of it as, but there are experts in the audience who can probably correct me on that. Good question. Something else? All right, so on this slide, I will find the stable equilibrium of Ising's original model. So Ernst Ising submitted an overview of his dissertation in 1924, but it did not appear in print until February of 1925, 100 years ago this month. So basically what he was considering, he was trying to find a model for ferromagnetism. So he considered simple spins, binary degrees of freedom that can be either up or down, and represented by sigma +1 or -1, with interactions only between nearest neighbors. And so low energy, minus sign here, when two spins are pointing in the same direction, and high energy when they're pointing in opposite directions. So this is the Hamiltonian he basically solved. It can also be written in terms of the energies of the number of bonds. So you have total number of bonds n minus j for all of them, except for the ones that are high energy, and -2 of those to get rid of the minus and make it a plus j for the high energy bonds. So you can write the energy for this one-dimensional system very simply in terms of just the bonds. And in fact, Ising did have basically, okay, so this slide will have a lot of mathematics on it, and so I'll apologize for that. But the basic idea of what I'm going to talk about, I'm going to start off with two different Hamiltonians and solve them in different ensembles. So sorry, what's cut off here. This is the nano-canonical ensemble. This is the canonical ensemble. Two different ensembles, they give the same answer. Different Hamiltonians, different ensembles, same answer. Okay, so there's going to be a lot of math between these boxes, but just remember the goal. Okay, so here's the original Ising Hamiltonian. You take that and put it into Boltzmann's factor with the multiplicity from the binomial coefficient for the, either low energy or high energy binary system binomial coefficient. You can do that sum, you get a Cauchy function. So that's actually in here. It's a little hard to read this old German script, but this is Cauchy of alpha. Alpha is the magnetic field, so we set that to equal to 0. So this becomes 1. Sinh of alpha is 0. So that here you have, square root of e to the -2 energy over kT, and so then you can turn that into a Cauchy, and it's raised to the n power. So that's basically his answer to this point. But then he summed over all different sizes. In his original paper, he summed over all different sizes. He called this a mathematical function just to prevent the summation from diverging. It's actually the chemical potential. When you put this spin system in contact with a bath of other spins, it's the chemical potential. And so this is the partition function. In the nano-canonical ensemble, we've taken two Legendre transforms to convert energy to temperature and number of particles to chemical potential. And now what do we do? The average size is given by a logarithm of this thing, but what is the chemical potential, or what is the temperature? You have two intensive environmental variables and nothing fixes the size. So the statistical mechanics doesn't tell you what the answer is. You have to look at the thermodynamics. And so that's what we've done here. Here's the Hill's subdivision potential. That's the slope of the energy, also the slope of the free energy. So we'll integrate that slope and find that this is the change in free energy as a function of the number of subdivisions. Sorry, more stuff cut off down here. The number of subdivisions. So when the number of subdivisions, so this is a system of 1,000 spins. And this is when you have 0 subdivisions, that means you have a homogeneous macroscopic system. And as you increase the number of subdivisions, the free energy goes down. It goes down to about twice below what it would have been without this term. So all of this is coming from subdividing a bulk sample into smaller and smaller bits. It reaches an equilibrium when the slope is 0. That means the subdivision potential equal to 0. So that means this is equal to 0. which gives you what the chemical potential should be, which gives you what the average size should be. Now, this makes sense because at infinite temperature, the average number of bonds in a system should go to 1, because at infinite temperature, it's dominated, the energy is insignificant at infinite temperature, so everything's dominated by entropy, and the entropy of made and broken bonds is the entropy of mixing maximum when you have half bonds made and half bonds broken. It also makes sense when temperature goes to 0, then you have an infinite homogeneous system as the temperature goes to 0. And so that makes sense. This is the thermal equilibrium of Ising's original model. So it's not surprising that Ising couldn't find this 40 years before Hill did his work. What's surprising and sad is that it took me 20 years from the time when I started working with Hill's work until I finally figured out how to find the thermal equilibrium of the Ising model. Another way to think about it is to think of an infinite system that subdivides into smaller parts. And so here's a different Hamiltonian. It looks similar, except the J's can be either 0 for missing bonds or non-interacting spins, or J for the interacting spins. And once again, you have the number of high energy bonds, subtracted 2 of those, just like you have over here, but then also -1 for the non-interacting bonds. So you have 3 components in this energy, and so you need the trinomial coefficient for these energies, and you sum over all the high energy bonds and all the no energy bonds, it doesn't matter which order, and you come up with a different partition function because you have a different Hamiltonian. In the canonical ensemble, the partition functions are different. However, you can find the average size of these small subdivisions inside the bulk sample, and then use percolation theory to get the same answer for the average size of the regions inside the sample. So different Hamiltonians, different ensembles, same answer. Okay, so now let's use that for non-classical critical scaling. So critical scaling is the divergence of various quantities at a critical temperature, at a critical point. And so the physicists are most familiar with, say, the Curie-Weiss law. So in thermal physics, you often work out the Curie-Weiss law. It was introduced by Pierre Weiss in 1907, and it assumes that you have correlations or infinite correlations. Every spin is basically interacting with every other spin, and you get out a mean field theory. And so the critical scaling has to do with how various thermal quantities diverge as you approach the critical temperature. So it's often governed by a scaling exponent, here gamma. So for the Weiss mean field theory, gamma is equal to 1. And so the Curie-Weiss law, I'm sure you've all seen that. It diverges. However, if measurements where you take, the way you determine this gamma is you take the logarithm of this function and look at the slope. The magnitude of the slope is this gamma as a function of temperature. Measurements on europium oxide and gadolinium look like this as a function of reduced temperature. So the Curie-Weiss law works fine as long as you're about at twice the critical temperature, the Curie temperature. It's a slope of about 1 up here. But as you get closer to the transition, it's definitely not 1. So it turns out that the idea of critical scaling was probably first introduced by van der Waals as part of the van der Waals equation for the critical point in liquid vapor systems. It yields classical critical scaling exponents as well. But in fact, as from this nice paper, it's found that van der Waals also was aware of non-classical critical scaling as early as 1893. So there were experiments being made in the laboratory of Chamberlin Onnes. This is Jules Emile Verschaffelt. He's one of the heroes of this story. He made some of the earliest measurements of non-classical critical scaling, and he spent most of his life measuring non-classical critical scaling. And van der Waals analyzed some of these data, but because there was no theoretical understanding of this result, he neglected them, he ignored them. And that served him well because he then won the Nobel Prize in 1910 for his classical scaling ideas. But what happened in 1944 was Onsager solved the two-dimensional Ising model and found a scaling exponent of 1.75 for the two-dimensional Ising model. And that's called the Onsager revolution, because now everyone believed that the exponents could be non-classical. By non-classical, I don't mean quantum. This just means not as old. So sorry about that confusion. Classical means old critical scaling. Non-classical is not as old critical scaling. Okay, but using this, the three-dimensional version, which cannot be solved analytically, but at least you can simulate it. You get the dashed line here. And renormalization group theory tells you that the gamma should go to 1.237 as the temperature goes to the critical point. But you see the data do not follow that. So this is the paper we published in the year 2000, used mean field theory. But instead of having an infinite mean field theory, it's on a finite cluster size. So you sum over all different sizes. Sorry, this is n summed from 2, I guess, to infinity, something like this. And this is m up to n, minus n. So m is the alignment, and this gives you the susceptibility. Anyway, so this is a function that we fit with mean field theory, but on finite-sized systems rather than infinite system, and we get this red line, these red curves. Okay. So, and if you make the more recent measurements show that clearly the scaling exponent as the critical temperature is approached is not 1.237 as expected from standard theory, but goes to 1 as expected from mean field theory. So there's 3 or 4 possible explanations for why theorists have not recognized these experiments. According to these quotes from these papers, one of the explanations is that theorists have continued their 130-year tradition of neglecting experiments. That's a little bit harsh, but it's a little bit consistent with another line in this conclusion of this paper. It says that when the best data are observed, taken on the best measurements, some of the exponents could agree with the theory, but most do not. So theorists could just simply be taking the best values for their theory. Another explanation is that this equation is too simple. And so there's no reason for a theorist to work with this equation because it's too simple. Even experimentalists can use this equation. But probably the best explanation is that there's not a simple understanding of how you can get mean field theory in one dimension. But in fact, by time averaging the one-dimensional Ising model in one dimension, by time averaging, you do get exactly mean field theory. Sorry, it's cut off from here. But it's just by averaging over the different states that are available without coupling to the heat bath. So that's consistent with the Hole-burning experiments where the system is only weakly coupled to the heat bath. You can get mean field theory not only in 4+ dimensions, which is the usual place, but also in one dimension with proper time averaging. Okay. Anyway, so that's it for the ferromagnetism. Now the rest of my talk is on the arrow of time. Any questions before I go on? I'm sorry. This is a thermal equilibrium amount of disorder. So you don't quench in any disorder. The disorder is formed to increase the entropy. I'd have to go back. So the disorder maximizes the entropy. To minimize the free energy in the nanocanonical ensemble, the system must put in these breaks in the interactions. The actual mechanism of it, I've been told it could be many-body localization, Anderson localization, or something like that on the wave functions. And so it's breaking the correlations somehow in the wave functions. That's the only thing I can suggest. Okay? So it's not quenched randomness. It's a thermal equilibrium distribution. So these are intermittent interactions that sometimes interact and they're moving around. That adds to the entropy to allow them to move around. Okay, on to the arrow of time then. So the arrow of time in our daily lives, the reason you can't go back and change your history, it comes from the second law of thermodynamics. It's the only place in basic physics that we encounter every day where there's a direction to time. And so to understand why, so this equation is a first order derivative with respect to time. So if you change the sign of time, it changes, whereas Newton's laws is second order derivative. And so you change the sign of time and it doesn't change. So Newton's laws look the same forward and backwards, whereas the second law of thermodynamics gives you the direction of time. But of course, you can reverse the arrow of time various ways. One way is to look on YouTube. And so, another important thing about maximum entropy that comes from the second law of thermodynamics is it's also necessary to define temperature. So a well-defined temperature indicates that the system has reached its maximum entropy. So that will be important as well. But anyway, so going to the YouTube to look at how you can reverse the arrow of time. So I believe Matt O'Dowd is a cosmologist, Australian cosmologist, if I understand correctly, but working in City University of New York. And so here he has the arrow of time and how to reverse it. And so here are 6 particles being governed by classical mechanics. And they start off with certain initial conditions. You can't tell whether it's going forward in time or backwards in time. But if they start off with these initial conditions and they start moving together, that looks like the entropy might be going down. If you start off with the particles spread widely and then they sort of coalesce or come together in the middle, that looks a little bit like entropy is being reduced. But then as time goes on, classical mechanics, right? So, so the usual assumption is that yes, you can get entropy, or a common assumption is yes, you can get entropy to decrease if you start off with the right initial conditions. Okay, and that comes from the concept of phase space. So entropy in classical systems, such as Newton's laws, is given by the volume in phase space. Phase space is velocity versus position, basically. And so if a system starts off in a well-defined velocity and position and spreads out from there, the phase space gets more ramified of the possible situations, gets more ramified, and so that's associated with entropy increase. But if this is an entropy increase, then you could simply reflect all the particles at this moment and get the entropy to decrease. And so that would violate the second law of thermodynamics, and that's Loschmidt's paradox. So if something is reversible, and if you reverse it in the middle of its progress, and if the entropy was increasing at first, the entropy would decrease afterwards. But all of this is given and assumed with knowledge that Liouville's theorem says that the volume of any system, the volume of phase space of any system that obeys Hamilton's dynamics cannot change. So the entropy of this system cannot change. The volume is staying the same. The entropy is staying the same. So what's going on here? Well, if you know where every particle is at all times, then there's no entropy ever. So what's happening is you really, for entropy to be a thing, you have to have just knowledge that the particles are in the box. You can't know where they are in the box, or else it would erase all the entropy. All you know is the particles are somewhere inside this box. You don't know whether they're far apart or close together. That's where entropy comes from, the missing information that you get from not looking inside the box. Okay, so then where does increase in entropy and maximum entropy come from for the second law of thermodynamics? Well, most people believe that it comes from complexity. So this was a simple enough system that it sort of looked like entropy was decreasing, but this is a complex enough system. We know that a cloud of dust does not turn into a skyscraper. So we know this is a film running backwards. And so most people believe that the reason we don't see this happen is not because the laws of physics are irreversible, but because the likelihood of a pile of dust turning into a skyscraper is extremely small. The initial conditions necessary for the system to start off in a cloud of dust and turn into a skyscraper are extremely rare. So it has to do with the unlikelihood of an initial condition having the entropy go down. Okay, but we will show a simple system from 2 particles up to the thermodynamic limit that also favors the arrow of time. So the system is, again, the Ising model, but with bonds that can be broken as well for the thermal equilibrium of the Ising model. This has periodic boundary conditions, so the interactions between these 2 spins and again around like this, so you can think of it as a ring or periodic boundary conditions. And first of all, let's couple it to a heat bath using the Metropolis algorithm. And we can know the entropy of the Ising system exactly by just counting the number of configurations and then using the equation on Boltzmann's tomb. So W for Wahrscheinlichkeit. For this configuration, there are 2 of them. It can be both spins up or both spins down. Both have the same energy of -2 units, -1, -2, -2 units. 2 configurations, 1, 2, gives an entropy of k log of 2. So for the given energy, entropy is k log of 2. Here, higher energy, both bonds high energy. Again, 2 configurations with that energy. Again, the entropy is k log of 2. Now, this system, there are 4 possible configurations. This and this with the bond, this bond not interacting, and the same too with this X over there. So their multiplicity is 4. And for any arbitrary system with number of bonds, number of 0 energy bonds, and number of high energy bonds, the multiplicity is given by this trinomial coefficient. So we can calculate the exact entropy of this system at any moment. But we cannot make this system reversible because it involves the Metropolis algorithm, which is intrinsically irreversible. So we have to make it simpler. And so instead of having an infinite bath, we consider a bath of Einstein oscillators. So this system is now a closed system consisting of the spin system and a heat bath, an explicit heat bath of Einstein oscillators. And energy has to be conserved. So the only way this spin can flip now is if there's enough energy in the bath to allow it to flip. This is a model introduced by Michael Kreutz, basically to get rid of the random number, which was a slow process in old computers. And so to get rid of the random number generator, he thought of this way of simulating the Ising model. So here it is, the energy going from -2 to +2. And that energy had to come from the bath. The energy of the bath goes from +4 to 0. Okay, so we know the entropy of the spin system. It's just as before, but now we also know the entropy of the bath. Oops. There are 5 ways to have a total amount of energy of 4 in this bath. There can be 4 and 0, 3 and 1, 2 and 2, 1 and 3, or 0 and 4. What did I say? 4? I meant 5. 5 ways to have 4 units of energy in the bath, the kinetic energy, bath energy. So the multiplicity of that is 5. Entropy is k log of 5. And so the sum of the entropies, you just multiply the multiplicities, k log of 10 for this state. Now there's only one way to have zero energy in both bath particles. So that's 1 is the multiplicity of this. Entropy of a logarithm of 1 is 0. But the product gives you logarithm of 2 for the two different configurations of the spin states, and so forth. On and on, you can calculate the exact entropy of the system and its bath at every step. Plus, it's reversible. Every time there's enough energy for the system to make it the transition, it will. There's no random number involved necessarily. So you can start off, run the system, and then run it backwards again. Okay, so that's what we'll do. Keep track of the entropy as a function of time. Rather than 2 particles, let's go with 2 million. Sorry. Let's go with 2 million. And again, we can calculate the entropy exactly. So here's entropy as a function of time in sweeps. So we run this simulation for 500 billion steps, invert the process, run it back for 500 billion steps. It follows the entropy exactly back down, every step down at the end of the trillion different steps. And so that's Loschmidt's paradox. If the entropy went up at short times, the entropy will go down when you reverse it at the end. That's for this reversible simulation. However, you can also put in randomness in which bath particle the system will couple to. And of course, that is not reversible. It's an irreversible process. Same system, but randomly choose which bath particle you will use for each step. Entropy goes up and never comes down. And if you look closely, it looks like it's a little bit higher in here. And indeed, by taking moving averages, so you can look closely at these tiny parts per million entropy difference, the entropy of the irreversible dynamics is significantly higher than for the reversible dynamics, at least 10 standard deviations higher. Furthermore, these simulations are done irreversible, reversible, irreversible, reversible. So the system starts off in a high entropy state. Every time you turn on reversibility, the entropy goes down. So this is a counterexample to the assumption that, that entropy increases because of the complexity of the initial condition. Every time you turn on reversible dynamics, the entropy goes down. Where does this entropy come from? We can look at the entropies of the spin system and the bath separately. The entropy of the spin system goes up when you turn on reversibility, opposite to the total entropy. So all of the entropy going down when you turn on reversibility comes from the heat bath. Therefore, of course, you will never see this in a metropolis algorithm, which you don't know the entropy of the bath and can never be made reversible anyway. So now we can look at the statistics of the heat bath and see if it makes sense with temperature. So we can just count the number of times a system is in each different level, look at the distribution. It should obey a Boltzmann distribution. Therefore, you look at the ratio of probabilities between 2 neighboring levels. The logarithm of that ratio gives you something inversely proportional to temperature. So you find a well-defined temperature for the bath only for irreversible systems, large and irreversible systems. For reversible dynamics, there are at least 2 different temperatures for odd and even levels in here. So you do not have a well-defined temperature if you have reversible dynamics. That's the reason the entropy goes down when you turn on reversible dynamics. So this is for in the thermodynamic limit. If you look at smaller systems here, 128 particles, you never have a well-defined temperature. That's because there's not enough energy to occupy the high energy states very well. So then as a function of size, here's the difference between the irreversible and the reversible entropy as a function of system size, starting at 2 particles, going up to 2 million particles. Entropy difference starts off at around 1% and goes down to parts per million in the thermodynamic limit, but it never goes to 0. So in the thermodynamic limit, it is stabilized and never gone to 0. Where is this irreversibility coming from in nature? Of course, in the computer simulations, it comes from a random number generator. But in nature, where does this intrinsic irreversibility come from if the second law of thermodynamics is to hold? Well, we speculate that it comes from the measurement process. So in the reversible dynamics, each spin couples to only one bath particle. There's no randomness. If, oops, the buttons here. So for the reversible system, it couples to only one heat bath particle. For the irreversible system, it can couple to either. And that's why it works only down to 2 particles. You can't have it for 1 particle because there's no randomness in choosing the energy of 1 particle. Even if you have only 2 particles and choose the particle randomly as if it was a quantum measurement process, then that's one possible speculation about where this intrinsic randomness may come from. So you don't need humans to make measurements. A spin system also can make these kind of quantum measurements as to which heat bath particle it will couple to. Okay, well, I'm running out of time, but fortunately, this is the final slide. So here's how the conservation of energy has progressed through the years, first written down clearly by Clausius in 1850. Gibbs' greatest contribution began when he introduced the chemical potential. Hill has introduced a mathematically similar subdivision potential that allows you to treat finite size effects in thermodynamics. And it can be called the most exhaustive addition to equilibrium thermodynamics since Gibbs. For instance, using just one section of one chapter of one book that he wrote, we have been able to find solutions, resolutions, or at least clarify several unsolved problems in physics listed here. So it's surprising to me that not many people have captured or have gotten interested in this result. And so here's one quote. It may be as with much of Carroll's work, it was simply ahead of its time, and in future years, much will be made of it. So what do we mean? So I'd like to give you an invitation to enter a new field of physics, finite size effects in thermal physics. And what does this mean by future years? Well, a prominent biophysicist came to visit some years ago, and he said, when I gave him something like this talk, he said, he actually knew Terrell Hill. He worked with Terrell Hill at the National Institutes of Health, but he hadn't heard of this small system thermodynamics. He said, very interesting. It may be right, but no one will use it for 100 years. And I think the reason he said that was because it's based upon thermodynamics and not statistical mechanics. And physicists don't trust thermodynamics. Okay, thank you for your attention.
In most practical applications. So I was wondering what additional practical applications
Well, it's so you're asking what additional practical applications? Well, for instance, what about heat flow, heat process in microprocessors, right? They still use classical thermodynamics. They still use finite element methods, boxes and heat resistors and things like that. They do not include local fluctuations and other things, which this could include. So as technology is reaching the 2 nanometer scale this year, it's supposed to get down to 2 nanometers in integrated circuits, this will become increasingly important to properly characterize the heat inside of microprocessors. and other integrated circuits.
Just make a comment, the 2 nanometer scale of quantum effects matter at room temperature as well, so.
No doubt.
Quantum entanglement might be relevant. Any other questions? Jose?
I have a small question, but it's kind of a technical point. So when you show the capacity of force, show the quantum device law, and then you made a couple, it's a kind of a measurements that kind of give you that. And you say, you talked, I don't know if it was an informal way of talking about it, but you talked about anharmonic modes. And so what does that mean? Because the way I view that is crystal has modes that are in every mode has some harmonics, but there are no extra anharmonic modes.
The best way I can answer that is from the molecular dynamics simulations. So these extra fluctuations come from atoms that are not at the bottom of the potential well, they're on the side of the potential well. So the anharmonic terms come from second neighbor interactions that are not at the bottom of the well, they're on the side of the well. If those atoms move coherently, their anharmonic effects will cancel, but they don't. And so all of this extra fluctuations comes from those second neighbor and third neighbor interactions. So it's not purely harmonic. There's some anharmonic terms that localize the fluctuations somehow, localize some of the fluctuations somehow. That's what I believe it is, but I'm happy to discuss it with you more if you have better ideas.
Just a comment there, our past colleague, John Page, of course, did some wonderful work on localized modes with very high amplitudes. Yeah, yeah.
Yep.
We forget the history of our departing colleagues, don't we? Any other questions? Well, thank you, Ralph. Let's thank Ralph for that.
Thank you. Thank you, sir.
Enjoyed that.
Did you?
Yes. You know, the interesting thing is,